we get a triangulated category. So this is a stable category. And stable module category. And we have the group cohomology acting. So remember, you can think of this as the X algebra of the trivial representation. Maybe you remember we have a tensor product, and the trivial representation is obviously the unit with respect to that tensor product. So we look basically at the graded endomorphisms of the unit, and this is acting on the stable module category. We have used that, so maybe I recall briefly. So last time, we have used that action already because we constructed these local cohomology functors. Local cohomology functors, which are denoted by gamma p for each prime. So these are endofunctors. And let me remind you that we always work with graded modules, meaning that this is actually a graded commutative ring. So then the graded homomorphisms in the stable module category will become graded modules over this ring. And in particular, then we localize and so on with respect to a prime ideal, and that will also be a homogeneous prime ideal. So P is always homogeneous prime. So it will be a prime ideal in spec. So this is a set of homogeneous primes. Prime ideals. Okay, and what did we gain from these local cohomology functors? We were able to define the support. So the support of a module M was by definition just the primes in the cohomology ring, so that gamma p M is non-zero. Yeah, and this is sometimes also called the small support. There was a brief discussion in my last lecture. I should think of this as a small s. Small support meaning it may well happen that the support of a module is just a singleton. Yeah? So for example, if we evaluate this functor, it's a trivial representation. So just an example. So the support of this trivial representation, the local cohomology of the trivial representation is just a singleton. For actually, I should be careful here for. No, I think it's true. Good. So what else? So what we actually gained, I mean, why did we look at the support? We get actually a classification of all localizing and thick tensor ideals of the stable module category. So that was our goal last time, classification of localizing and thick tensor ideals of the big stable category, but we had also a statement for the small stable category. Okay, and today we want to discuss local duality. It is just, the support is just a singleton P. Yeah, so the support, of course, is always a subset of spec. Yeah, so it's always a subset, and yeah, so I really mean the set just containing the prime P. No, this is good that you ask. That is for any prime ideal, whether it's maximal or not. And this is what sometimes is referred to as a small support. Yeah, so it's not necessarily closed or specialization closed. Yeah? So this is sort of a feature of this local cohomology functors. Yeah? And we have seen actually that this classification of localizing subcategories was really in terms of all subsets of spec R. So I often denoted that by R. Also today I will use R. So all subsets arise basically as support. Okay, so no. Just to fix that. So last time, the derived category is somewhat uninteresting, meaning the following. Yeah. So I had this recommand, and if we look at the, so that was the homotopy category of chain complexes of injective KG modules. Inside we have the acyclic ones. And this is actually equivalent to the stable module category. And then we have here the derived category of all KG modules. And when I say it is the uninteresting part, I mean that we basically care about this, the stable category. Here we have actually this sort of recommand, meaning these functors have adjoint. So the big category is glued from small categories, and the support, if we look here at the support, here we have just the positive degree elements. So the objects here, using this notion of support, are all have support the maximal ideal, or zero. Yeah? Of course, if we take the zero object, the support will be zero. Yeah? But if we take a non-zero object here, the support will be this. Here we get all subsets, basically. So here we have sort of all of spec. And here we have the support proj of R, so meaning spec R without this maximal ideal. So meaning that the support of the modules here will be, they will be subsets of proj. Yeah. Does that sort of roughly answer your question, because you were wondering about the derived category? Mm-hmm. Mm-hmm. Yeah. The cohomology ring, yeah. And what else do you mean? Yeah, of course, sure. KG is sort of our sort of central object in a sense. But I mean, the point is that this in general is not commutative. The group algebra will in general not be, if the group G is not an abelian group, then the group algebra will not be commutative ring. But these actions which we are using, they are given by some commutative ring, rated commutative ring. That's right, yeah. Good. So let me remind you also about our notation for modules Mn. For two modules, I want to use this notation here. So the graded morphisms this was just the direct sum of the hom underline M omega inverse minus I n. So when I talk about the graded homs, I mean that I take the sum of all the different degrees, and remember that omega inverse is the suspension. So we have a triangulated category with a shift or suspension, and this is omega inverse, which is the inverse. This is a suspension. So inverse syzygy. If omega is the syzygy of a module, we take sort of the dual construction, and that's the inverse omega. Just to give you some picture here about how to relate this to X. So the stable morphisms, omega minus I, so in degree n, in degree I, which is given by omega minus I, this is so-called X isomorphic to the Tate X of M and N. And just to give you an idea, so everything is here over the group algebra, right? And this is the usual X. Okay, so now we talk here about X in degree I. This is the usual X. If I is greater than 0, if I equals 0, we get the stable homomorphisms from M to N. And so but we have also negative cohomology negative degrees. And one way to understand that is state duality. So if we want to compute the negative degrees, we can use that duality. But this is only for finite dimensional modules. So this is isomorphic to hom n omega m. Yeah, and of course you can in that way compute sorry, here also underline. In that way, you can compute the negative degrees of Tate cohomology, because here we have the degree -1, basically. It's a dual of, yeah, degree -1 is a dual of degree 1. So this is Tate duality. Okay. Yeah, I guess I should state already my first theorem, which is actually not mine, but rather a theorem of Dave Benson and John Greenlees. So what do you mean by local duality? I mean, this is the first theorem. So Benson, John Greenlees proved this. I think it's published 2008. So for module M, arbitrary KG module, and actually maybe I want to think of it as an object in the stable module category, so that doesn't make a difference. And P, a prime in Proj, so non-maximal prime. We have this formula for Tate X with gamma P of K. This is isomorphic to So remember, I wanted to denote the cohomology ring by R. The dual, some sort of Tate dual. Here I take degree -d minus I of the cohomology with coefficients in M, and take its dual. And I should explain what I mean, where, so this is for all integers, where IP just is the injective envelope of the ring R modulo the prime ideal. Remember, everything is homogeneous, yeah? So homogeneous prime ideal, we take the injective envelope of this quotient, and D is the Krull dimension. So the shift which comes up is the Krull dimension of this ring, R localized at P. No. No, this is the usual cohomology. Yeah, we're working here away from the maximal idea. Yeah, one could also put here Tate. Yeah. But as Shrikant says, it doesn't matter. And maybe, in case I haven't explained this, so when I write this, I mean X of the trivial representation with, so the usual cohomology with coefficients in a representation M means, I mean, one way of defining it is the X with the M in the second variable. This is also KG, yes. Mm-hmm. That was my local cohomology functor. That's a good, yeah. So the local cohomology functor comes up again, but remember, I mean, I tried to explain how this is constructed or how one can think of it. And I agree it's somewhat abstract. And now if you look at this formula, you get actually this object here as a representing object of a fairly reasonable functor. Yeah? So, I mean, this is another way of thinking of this local cohomology of the trivial representation. Let me write that as a remark. I have actually several remarks. So the formula characterizes gamma p of the trivial representation as representing object of some very natural functor, of a cohomological functor from the stable module category into abelian groups. Namely, if you sort of take that functor here, so you take group cohomology and hom into this injective, you get a functor which takes coproducts into products, and it is exact. And then Brown representability tells us there is a representing object. And that representing object is this one. Yeah? So that's my first comment. So, of course, the algebraic geometrists notice this is very much similar to Serre duality. And we have seen lectures about this. So my second comment. So the formula is an analog. Of Serre duality. And what do I mean? So I take a scheme. So the formula which you find, say, in Hartshorne for the X groups of a coherent sheaf with the dualizing sheaf, that this is equivalent to the K-dual of the cohomology of the sheaf minus, n minus 1, n minus I, X with coefficients in F, sheaf cohomology, and its dual with respect to K. Yeah, so this is for projective non-singular variety scheme of dimension n over K. Yeah? So now if you compare these formulas, I mean, there's really an obvious analogy. The point here is that we take the action here of the cohomology ring. I mean, here it's just the field, but otherwise there's this kind of analogy, and you see, of course, the role of the dualizing sheaf is played here by this object here. well, that's it's. I mean, one way of thinking of it is I told you we have here a functor which is defined on the stable module category. Yeah, and it is representable, and the representing object is then somewhat. So it means that this functor is representable means it is of that form, hom blank, and here is the representing object. Yeah, here's a representing object, and it is actually, now I need to be careful, omega I of gamma p, no, omega minus I, of course. Yeah, so this is a representing object, but we need to take X. Yeah, we have also homomorphisms in negative degrees. Yeah, so that was my. Yeah, so we're in the stable category. Yeah. Are there further questions? Another comment about this sort of dualizing object here. I told you the functor, the local cohomology functor, of course, is defined on the whole category. Yeah, and gamma p of a module can actually be computed by just taking the module and tensor with gamma p of the trivial representation. Yeah, because it's a tensor functor. It is a tensor functor, and so you need to know only how it acts on the unit of the tensor category. And in that sense, this situation is sort of good enough to get back the whole functor, basically. My third comment, last comment, remark, there's also a version for finite group schemes. And this is why I'm referring here to this joint work with Dave Benson, Shrikant, and Julia Pevtsova. So all what I'm talking about is basically from that paper. There's also a follow-up paper, but yeah, the result first was proved by these two gentlemen, and there is then a generalization to group schemes. Yeah, so finite groups sort of generalize to group schemes, and then one has sort of an additional sort of character playing a role here, which is trivial when one is just dealing with a group. So also, I mean, John may explain more about it, but I mean, the way it was originally proved was using sort of a Gorenstein duality for cochains on BG. So, so this proof uses Gorenstein duality for cochains on BG. The approach which we used in our work is quite different, and therefore I think one is invited to compare. Even though I will not say too much about the proof. What I want to do instead, I want to give you really, oops, I should not have erased that. Well, I give you an example. I think the first non-trivial example is always the Klein foregroup in characteristic 2. Yeah, so I mentioned it before. So example. Yeah, I mean, this is the smallest example of smallest interesting example of an elementary abelian P group. No, you asked for elementary abelian, right? Ah, okay. Let's try to explain Klein foregroup. So, of course, in characteristic 2, and then how can we think of this? So, what is gamma p of k? Yeah, and so we remember the approach. So R, the cohomology ring, is basically given by two variables, the polynomial graded polynomial ring, the polynomial ring, which we view as a graded ring in two variables, the degree of the theta i's equals 1. So meaning that Proch of R is just identifies with P1. Yeah, and now we take sort of a closed point. And you remember I defined this L zeta modules. So for each prime, so P now sort of prime not 0 and not the maximal idea. We defined the module LP to the R, and that was basically the co-kernel defined as a co-kernel of the map from K into omega inverse minus d R of K, where this element is sort of generates the prime. So this is in Hom K omega minus d R K. And we think of this as X dr of K, comma K. So a homogeneous element. So this is a homogeneous element which generates that prime ideal. Yeah? So let's call it P to the R. And the prime ideal P is generated by this element pi. Yeah? So we have a generator. I mean, it's all very explicit in that case. So we have a generator, and these modules are sort of constructed from these generators in the cohomology ring. And now the point is that we have actually a nice chain of inclusions of these modules. And we can take its sort of union or colimit, and this is exactly gamma P of K. Yeah? So that's one way. I mean, it is sort of similar to the actual construction of the local cohomology functor. I mean, the cellularization, which was mentioned before. But here you can do it sort of very explicitly. Yeah, I mean, you see, it's a domain. So the prime ideals are generated by a single element. No, it's a principal ideal. Yeah. No. Yeah. Yeah. So this generator, I mean, the prime ideal is supposed to generate, say, is in degree D, and therefore it is, we can think of it as a sort of map from K to omega minus D, and if we take now powers, we get into D minus R. That's the way I'm thinking of it. No, it's just an element. It's just an element, yeah. Mm-hmm. Ah, yeah. By generation, I really meant here generation for the prime ideal. Yeah. Okay, so maybe I should go on, because I wanted to tell you, I wanted to give you another version of what I call local cell duality. Okay, so yeah, I should remind you about this definition of Bondal-Kapranov. Bondal-Kapranov, it's actually from 89. So let's suppose R is a commutative ring. And D the madness duality, which you remember I discussed my first lecture, and T an R-linear triangulated category, and suppose T is Hom-finite. Hom-finite. And by Hom-finite, I mean that the Hom groups have finite lengths. So Hom between two objects, x, y, has finite lengths. Lengths over R for all objects x and y and t. So what is a cell functor? A cell functor is an equivalence say F equivalence of triangulated categories together with natural isomorphisms, isos from D Hom x, y to Hom y dx. So it is actually sufficient to assume that we have an equivalence given with such natural isomorphisms, and one can show it is actually preserving the triangulated structure. But that's not so important. Okay, and I want to recall also from last time that we have cell duality for finite dimensional algebras only when, for the bounded derived category, only when the global dimension of the algebra is finite. Okay, so recall. So if A is an Artin R algebra, so R was a commutative ring, then dB mod A, more or less by definition, it is a homofinite category because the homomorphism groups over an Artin algebra have finite lengths over the ring R. That's basically the definition of an Artin. You have a question? Oops, yeah. Yeah, thank you very much. Thank you. Yeah. Mm-hmm. It's a covariant functor. It's a covariant functor, yeah. Mm-hmm. So I mentioned that this is a homofinite category, and then we have that the bounded derived category is homofinite. Homofinite. And dB mod A has a cell functor if and only if the global dimension of A is finite. Now, if we care about group algebras, then this is usually not the case. Yeah, if the group algebra is not semi-simple, the global dimension will be infinite. And the semi-simple case is somehow the non-interesting case. So dB mod kg has no cell functor, except when kg semi-simple. Semi-simple. Nonetheless, we have local cell functors, and this is from a result from this joint paper, which I mentioned over there. For R now, the group cohomology acting on the derived category, the R-linear category dB mod kg has local cell functor, has a local cell functor for each prime in prod of R. So each homogeneous prime ideal, which is not maximal, we have a local version of this category, and we have a cell functor. This is not a precise statement because I need to explain what means a local cell functor. Yeah? And this is what I want to do. Yeah? So the message is the category, the bounded derived category has sort of globally not a cell functor, but locally it does have a cell functor. And that requires that I explain you now this, what I mean here by local. And I want to give you sort of a general definition because this is a there is a more general phenomenon behind this. It is, yeah, it's not only some result about group algebras, there's something more general. So here is a definition now. It's a bit longer. So R is a graded commutative, say, Noetherian ring. So basically, I want to generalize the definition of Bondal-Kapranov and want to take a graded ring now. Here we have just a ring basically sort of concentrated in degree 0. I want a graded commutative Noetherian ring. And T an R-linear triangulated category. And I want to assume Noetherianness such that the graded morphisms are Noetherian. Noetherian or finally generated over R for all objects X and Y in T. Okay, so then for a prime in spec R, I want to define the localized category that TP, the localized category, the triangulated category, given by the following. I keep the objects as usual. If I localize a category, I always keep the objects and only change the morphisms. So what are the morphisms? Well, I change the graded morphisms in the following way. I just localize them. Yeah? The obvious thing to do. So I take the graded morphisms and localize them at the prime P. Yeah? Because it's an R module, I can localize it. Everything is graded. So that's the localization at the prime P. And the triangulated structure is just induced from T. Triangulated structure on this category induced via, there's a canonical functor from T, sort of the localization functor from T to this localized category. And the exact triangles are those which are here in that category, are those which come from exact triangles here. Yeah? So images and all triangles which are isomorphic to images of exact triangles. Okay, so this is the localization. And remember the construction of the local cohomology functor. We first localized and then we take the P torsion objects. And we do exactly the same here. So inside that localized category, we take Hom star, the graded Homs. So Hom star was always in a triangulated category from X to suspensions of Y. Sigma is a suspension, so I can take negative and positive suspensions. Yeah, but I mean, to make sense, I mean, here's this, we can only localize graded modules. This is a reason. This is a reason. If you want now the Homs in degree 0, you just take this and take the degree 0 part. Yeah, it's sort of a bit hidden, but yeah. Okay. So inside, we want now to define gamma pt as a 6 subcategory. So a 6 subcategory. Given by, well, what are the objects? So it's a full, I mean, 6 subcategories are by definition full subcategories, given by the object X in this localized category, so that the endomorphisms, graded endomorphisms of X are p-torsion. So this is p-torsion. This p-torsion, and so of finite lengths over the localized ring Rp. Yeah, so we take sort of the finite length object. Remember, we started with Noetherian modules, and then Noetherian and torsion with respect to the maxima ideal is finite length. Okay, so we want to look at these sort of localized, p-local p-torsion subcategories for a given category T. So now I give you the definition of a self-functor in this setting. So R is now a graded commutative local ring with maximal ideal M, and a self-functor is an equivalence for an R-linear Hom-finite triangulated category so a self-functor for Hom-finite, an R-linear Hom-finite triangulated category is an equivalence F with natural isomorphisms. So this is now the variation of the Boндar-Kapranov definition. So I take the graded, so the graded morphisms in T, X, Y, and map into the injective cogenerator, because it's we have a maximal ideal. I mean, it is a local ring with a unique maximal ideal. So we take the injective envelope modulo Zx maximal ideal, and we get an injective cogenerator. And this is isomorphic to, okay, so I have here a graded module. I have here a graded module. But what I get now is just an abelian group, basically. But it is, also an R module, of course, but not graded. So this is now just the morphisms in degree 0. One could have defined that differently, but I think this is a convenient, the appropriate definition for our purpose. IFM is the injective envelope of ring modulo maximal ideal. Yeah, we only look at the maximal ideal. So here we have a local ring. So it's a local ring, and we have a maximal ideal. So this is the sort of the matless duality. I want basically, so this gives, so this is the injective envelope. And this is then hom. So hom into this IM is matless duality. It's some sort of matless duality. I should be a little bit careful here because, yeah, I mean, what I get is only an R module, but not graded in a sense, yeah.
IM is concentrated in degree 0.
No.
Side is graded.
No.
No, when you write hom R,
yeah.
Star XY. IM is a graded module.
Yeah.
Degree 0 only.
No. IM is in all degrees. I mean, R is a graded ring. This is a graded module. This is a graded module. And now I take just the homs sort of in the category. And that is sort of just in a being group a priori, but it's also an R module. Oh, it's an R module. Yeah. No, the previous definition, I was taking everything only in degree 0, basically. I was taking a ring, but not a graded ring. I mean, the Bondal-Krapanov definition is just taking, now I want graded modules, yeah. So, and now sort of a reformulation of that theorem. I mean, it took me some while to really explain what I mean with these local self-functors. So gamma p, this localized and p-local p-torsion category of KG module, bounded derived category of KG modules, has a self-functor. There's a self-functor for each prime p in watch of the cohomology ring. A little comment here that was already mentioned. Maybe, yeah. When I take this category, I mean this p-local p-torsion category, if I apply this construction gamma p to my category, this is actually equivalent to gamma p applied to the stable module category of finite dimensional modules. Yeah. And this is somewhat maybe consistent with the fact that we have self-functors, a self-functor for the stable module category. Yeah, I mean, the result here was that for a finite dimensional algebra, we have for the bounded derived category, in general, no self-functor, only if the global dimension is finite. So we don't have for the full bounded derived category, but as soon as we localize away sort of with respect to a prime, we get self-functors. So this is then actually, because we localize away with respect to a non-maximal prime, we also kill the projective modules, basically. We kill the projective modules because they are supported at the maximal prime, and therefore we could equally well localize the stable module category. Are there any questions? I hope sort of the picture is clear. I mean, the central message is that we use the action of the cohomology ring in a clever way. Yeah. Yeah. So maybe you remember. Yeah, that's a good point. I wanted to get to that. Maybe.
Is the existence important or the construction?
Maybe both. I don't know how to separate that. The functor is actually sort of induced by some global functor. I try to explain it. Sort of the last 10 minutes will be devoted exactly to explain where that functor comes from. It comes from the Nakayama functor, yeah. But then that it provides an that one has that sort of isomorphism here. Where is it here? This is sort of the hard work in a sense, and just to proof uses a passage to close points. So what do I mean? So I basically via an extension of the field we are working with. Yeah, so we take, given our, for fixed prime, so for each prime in the cohomology ring, we choose an appropriate big extension. And then there's, for that field extension, we can of course look also at the at KG. We can also look at the cohomology, and we find actually inside sort of a maximal ideal sitting over the P in Hodge. Yeah, so we pass then to a close point. Yeah, with respect, yeah. And at the end, this formula here boils down to Tate duality, meaning that we deal with finite dimensional modules, roughly speaking. Yeah, because we pass to a close point, and then these sort of modules we are looking at in this category, they become sort of identified as finite dimensional modules, but over this capital K. Yeah. I mean, this is sort of a very rough idea, and I'm not going into further details, and rather try to tell you how there is a global functor sort of behind. Yeah, so I wanted actually, I mean, originally I wanted to talk about local duality or Gorenstein algebras. So basically from group algebras to more general situations. That was my point. The result was not special for group algebras. Yeah? So if K is a field and A a finite dimensional K algebra, so K always a field, then we assume that A is Gorenstein. A is, suppose A is Gorenstein or Iwanaga Gorenstein. So the injective dimensions of A are finite on the left and on the right. And then we can actually take, so we replace now the group cohomology by Hochschild cohomology. We can take the Hochschild cohomology of A with coefficients in K, which is by definition the extra algebra over the enveloping algebra of A. So, so the X algebra where A E is the enveloping algebra. So this is the enveloping algebra. And here we're talking about Hochschild cohomology. And Hochschild cohomology is acting, R is acting on the bounded derived category of finitely generated modules. Yeah, roughly, so Hochschild cohomology has sort of a natural map into the X algebra for any module by just taking the tensor product. Yeah, so if I have an element here in Hochschild cohomology, I can think of it as a self-extension of, say, some homogeneous degree D, say, and then I tensor that with M and get here a natural map. And by this map, I get an action of the ring R on, so for any R module M. Yeah, of course. I mean, the algebra is a, yeah, sure. No, I mean, A has a left action and a right action. And I think now in terms of bimodules. So in the modules over the enveloping algebra identify with bimodules. There's somewhere an open, you mean? Yeah, if you want to be picky. Of course, we should be picky. We're mathematicians. Yeah, good point. Thank you. Okay. So remember, we have this Nakayama functor. And because it is a Gorenstein algebra, it is the Nakayama functor, the derived Nakayama functor gives us an equivalence. So it takes a module M, or complex rather, complex M, to the derived, what do you mean? D of A. So the derived Nakayama functor, so the dual, remember D is here now the vector space dual. So this is sort of the dualizing object for us, and this is the Nakayama functor. And this induces local self-functors. And yeah, I have maybe a couple of minutes left to explain what I mean. Under sufficient assumptions, so choose R subring, for example, with appropriate assumptions. So for example, that R is finitely generated K algebra, because Hochschild cohomology in general will not be finitely generated. I mean, this is not as for group cohomology, which is finitely generated, but Hochschild cohomology in general is not. So we take R, a finitely generated K subalgebra, finitely generated, graded of course. And we assume connected and maybe with connected degree 0 part is just K. And for any prime in spec R without the maximal idea, we have again sort of the same construction of a local cohomology functor for the Gorenstein projective modules. Yeah, so the ring R is acting on the category of Gorenstein projective modules, or the stable category of Gorenstein projective modules. And now we get two versions. So here are two theorems again from this joint work. The first one is that if I compute xmn hom over R into IP, again the injective envelope, so Mn are Gorenstein projective modules, and M is actually finite dimensional. So this is the same as hom underlined of n into omega d. D is the Krull dimension of the ring, gamma p, Gorenstein projective approximation of Nakayama functor of n. M, the finite dimensional one. Exactly, M is finite dimensional, so that makes sense. I can apply the Nakayama functor because the Nakayama functor induces a functor on the Gorenstein projective modules. And this is somehow the self functor which one sort of gets in a sense. It is basically induced by the Nakayama functor with the appropriate modifications. Yeah? D, again, the Krull dimension, and the gamma p is used as well. GP of module M is the Gorenstein projective approximation. So this is something I mentioned in my first talk, yeah, because a module has, I mean, this is sort of in the sense of Ausländerbuchweiz, and maybe one more, because this is sort of the analog of the first result I was presenting, the analog of the local self functors. I'm almost done, I'm sorry, but just sort of the local self functor for sort of, I take gamma p of dB mod A to gamma b dB mod A, and then this induces a local self functor, but maybe I leave it like that. Thank you very much.